Today I'm talking about implementation quantum circuit for ECDLP. So this is my yeah, my content, and then yeah, actually my name is Jung Bin Jo, and I'm Yonsei University undergrad student, and my major is physics. I'm then I'm interested in machine learning, reinforcement learning, QML, VK, and so on. So, and I think everyone in midterm exam, so I will try to very fast. So, yeah, it is a it is a sure quantum circuit. So, yeah, this is very popular. Um, Actually, this a similar problem is a factoring problem, discrete logarithm problem, and period finding problem like this. So today I'll talk about discrete logarithm problem, especially on elliptic curve. Then what is the elliptic curve? Yeah, actually, yeah, this one is a elliptic curve. It is a very similar to elliptic equation. So this just a smooth and no singular and other variety. Yeah, so this application is elliptic curve cryptography. So, and then actually this one is have a strange calculation. So like this. Yeah, this one is a elliptic curve point addition like this. Uh, yeah, this one is a P plus Q is a yeah this point is a R prime. Then P plus Q equal R prime. Very strange point addition. So we use this one for cryptography. So yeah, so just a little calculation. It is very easy. So just like this in calculation, then we can find the yeah, just calculation, and we have this result. I think yeah, like this. Yeah. So we can find point R like this. So yeah, it is very easy calculation. Just to yourself. So it is based on ECDLP like this. Yeah, so and then this one is a modular arithmetic using modular arithmetic. So it is a finite group, yeah, like this. And then it is a very difficult, oh, very difficult to solving this problem because we don't have a efficient solving algorithm for DLP. And then a point addition is like this. We 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 want to find this k, but it is difficult for on classical algorithm. So we need a modular arithmetic for this one for quantum circuits. So and modular arithmetic is like this, and then it is just a little definition, and then I think it is a little important modular inversion, and uh, we this is a modular inversion problem, so we just find this one, and then this one is uh today I will review paper. So this is just yes, this one, and then this paper uh present design to modular arithmetic quantum circuit for AC calculation and estimate this one. But today I'll talk about like this. So yes, start. Um, actually, this paper using QSharp, but I'm using on QISCA. So I use just just triple adder and integer comparator and swap like this, and then there's a URL link. If you want, just check, and yeah, like this. So there's a mod there's a paper, and this one is I make it, and it is a result. So uh yeah, actually I just copy this one, all of them, and then just apply my circuit. And in this pres- process, I use reparator or integer comparator, and yeah, more like this. And this one is a would reparator inversion, reparator like this. More like this. Inversion is a inverse way. So then and so on. Yeah. So I used Elisa modular inversion. I, so inversion, yes. And then this is a modular doubler. So just a swap and inverse and adder like this result. And then modular multiplication. This one is a combination of modular doubling and modular addition, just like this, and just copy it and applying. And then it is also just a copy and paste it my quantum circuit. So yeah, like this. And then actually it is a very hard modular inverse if you want, and just trying this 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 problem. So this is difficult for me. So yes. And then this one is a GitHub. This one is a paper, and then this one is just my quantum circuit code. for Qiskit. So if you want, and go and check. And actually, this one is a very problem because in this one is not unitary. So actually, this one is not quantum circuit. So it is a very problem, and I don't have no idea for. So just if you want and modifying my code, I recommend. Yeah, so thank you.
Okay, thank you, Jongbin Zhou, for your great presentation. And we'll take questions from the Journal Club first, and then we'll move on to the interactive seminar. So if you have questions for Jongbin Zhou, feel free to ask questions.
Okay, thank you for your great presentation. Can you hear me?
Yes, I
Yes,
can
we
hear you.
can.
Okay, so I first have a question about the journal club about superconducting quantum circuits. I'm a theorist, so I know nothing about experiments. So could you please just explain me what the negative frequency domain exactly means in the like error models, like you show one over f noises and uh,
Uh,
Ernest noises and Nyquist noises and so on.
um, actually, it is very common in the signal processing in the electrical engineering. So, negative frequencies means they also have negative domain in the um Fourier space in the frequency domain. So, um, well, I can explain it better in my
Okay, so
opinion.
it's in the Fourier space.
Yes, I think.
Yeah, okay. So if you transform like time domain into Fourier space, then you get a negative. Okay, thank you.
Yes, yes. Um, Question from me. Why is a high Q factor required in superconducting quantum computers? From the perspective of a classical RF circuit designer, for example, when we design amplifiers, we usually aim for lower Q factors to achieve wider operational bandwidth through impedance matching. Since I'm not familiar with designing for high Q factors, I wanted to ask about this. Okay, yes. In if you heard about the electronic circuits too, we usually design about us lowering the Q factors of the circuits because we want a wider operational bandwidth. Like amplifier, if we have lower Q factor, we can amplify the wide wide bandwidth, so it can be good amplifier. But in the superconducting qubits, we have I know the parts of the superconductings are divided by two. First one is just restoring the information circuits. In the kind of Josephson junction, we have some quantum information in that junction, so um, we should conserve this information. So if we have a low Q factor in this unharmonic oscillator, we lose our information in this circuit. So in RF circuit is different part of um, these superconducting qubits, it's the readout circuits. So I know they are different part of the superconducting qubits. For the Josephson junction part is just restoring the information, and readout circuit is about the amplifiers or the RF circuits should have low Q factors. It can be answered. Thank you. Do you have any questions about the ECC? Uh, if you don't have questions, can we finish this presentation?
Okay, thank you both presenters for your excellent presentations. And let me end this speech by introducing the Journal Club speakers because we couldn't do that for technical problems. Okay. And Jongbin Jo from QIA, who presented the Journal Club, is a junior undergraduate in the Department of Physics at Yonsei University. Last winter, he has done research intern at Multi-Physics Modeling and Computation Lab, led by Professor Jung-Il Choi in the School of Mathematics and Computing and the Department of Battery Engineering at Yonsei University. His main research interest is quantum computing, numerical analysis, AI, crypto, and stock markets. Thank you both people for your excellent speech. I apologize today for the technical problems.